If you go out to a very dark place and lie down on the grass and stare up at the sky, it looks like you're seeing millions of stars. In fact, it turns out you can only see about 2,000 stars at any given time with your naked eye, but it's still a lot. And those stars all have very specific positions. Some of them are bright, some of them are faint. And if you're in a really dark place, you can see that some of them are tilted a little bit to the red and some of them are tinted a little bit to the blue. And if you come back the next day and lie down in the same place and look up at the sky, you'll see all of the stars in exactly the same locations with exactly the same brightness ratios and exactly the same color tints. And if you come back in 50 years, which may be pushing it for some of you, and lie down in the same place, you'll see exactly the same stars in exactly the same place with exactly the same brightness ratios and exactly the same color prints. Now this gives you an image of a placid and completely unchanging universe. But nothing could be further from the truth. In fact, stars are born in regions of dark clouds of gas and dust in our galaxy and others. They form planetary disks. You see this beautiful star in formation right in the center where the disk of material that's turning into planets around that star. They eventually push away their natal material, as this cluster of stars is doing here. They then live out a long and sort of boring middle age with a bunch of companions, and then end their lives by blowing off about half of their material, leaving behind a stellar corpse called a white dwarf in the center. And if you tell me the mass of a star when it forms, I can tell you to within 1% exactly when it's going to die, which is better than I can do for myself, actually, which may be just as well. But nonetheless, the point is that stars have a life cycle of birth, middle age, and death, which we understand exquisitely well. It's just that the time scale for this life cycle ranges from, for the most massive stars, a few million years, and for stars like our sun, 10 billion years, and for the very smallest stars, more than 100 billion years. That is much more than the age of the current universe. So when you look up at the sky, it seems placid because the time scale for the evolution of most of these objects is very long compared to a human lifespan. But that's not completely true. If you look up at the sky with a telescope, you see lots of stuff going on much shorter timescales. If we want to look for things that are changing in some way, then we need a movie of the universe. And that's what the Vera C. Rubin telescope is going to do in providing us a legacy survey of space and time. Some things change much more quickly than stellar evolution. They move, they erupt, they eclipse, they magnify, they explode. So we really need a movie. That little arrow points to a little dot. It looks like all the other little dots, so you think it's probably a star. But in fact, it's not a star. It's a rock that's only about 5 million kilometers away. It's a few meters, tens of meters across, and it's moving. And if we take a time-lapse photograph, we see all the other stars are sitting still, but this object is moving across the sky. This is an asteroid in our solar system orbiting the sun. And some of these asteroids occasionally end up colliding with the Earth, which produced a real disaster about 63 million years ago, wiping out the dinosaurs. Good news for mammals, that's why we're here today, but it doesn't mean that won't happen again. And in fact, here's a picture, a remarkable picture that was caught. You see the same 4 stellar patterns there from the same 4 snapshots, but you see that faint little object moving across the sky just a few hours before it crashed into Earth on September 6th in 2024. In fact, it came into the atmosphere above the Philippines. No one saw it as a bright shooting star because it was very cloudy, but nonetheless, it burned up in the atmosphere. And this is the first time that we've actually caught something that collided with the Earth the same day. But there are lots, that is, millions of these rocks floating around in space, and they occasionally hit the Earth. Knowing where they are, calculating their orbits, and knowing which ones we need to worry about is certainly a valuable asset And that's what a movie of the sky will give us. And then there are comets. They're different than asteroids. Comets form far, far from the sun, 1,000 times the distance of the Earth to the sun. And they're big, sort of dirty snowballs. And they come into the solar system sometimes only once, orbit the sun, and they got flung back to the cold reaches of outer interstellar space. But they also, in principle, can collide with Earth. Then there's stellar flares. So here's a picture of the sun. The sun has these intense magnetic storms on the surface, which we call sunspots, but occasionally these storms have their magnetic fields twisted up and colliding with each other, generating plasma at a temperature of millions of degrees and shooting some of it completely off into space. These are solar coronal mass ejections, and they're really serious problems for our satellite network and even our power stations on Earth. In 1859, one of these flares shut down the entire telegraph network of the Earth. If one of those flares hit us today, it would be curtains. But these eruptions on the surface of the sun are fairly impressive and happen on timescales of minutes to hours. The sun, however, is by far not the most active of these stars. Here's the very nearest star to us, Proxima Centauri, only 4.4 light years away, and it had a solar flare recently that was 100 times the largest solar flare we've ever seen from our sun. When stars like Proxima Centauri and many, many other stars around us undergo these flares, the star suddenly brightens up for minutes to maybe an hour and then fades back to view. We could only see that if we had a movie. In fact, many stars are variable for a variety of reasons, both intrinsic and extrinsic. Extrinsic reasons is because many stars have a companion. Eclipsing binary stars come around with a very regular period, and they orbit around each other, and as they do so, when this star is in front of this star, it blocks it out, and when this star is in front of this star, it blocks some light out. There are other stars that are brighter on one side than the other, and they're rotating, and so as they rotate, we see them change. But there are lots of stars that are intrinsically variable. Either they're pulsating, they suddenly rise to a bright magnitude, and then they gradually, slowly fade from view, and then they pop back up again in a very regular pulsation period. The erupting stars go up and down quickly in a matter of days, whereas exploding stars that destroy the entire star last for tens to hundreds of days. Some of these erupting stars are called novae because there'll be nothing in the sky and then all of a sudden a star appears. The Chinese called these guest stars in ancient times because they come for a while and then they leave. We now know that these stars consist of a white dwarf, the corpse of a sun-like star, orbiting a red giant massive star. The intense gravitational field of the white dwarf draws matter off the surface of the other star, and as it falls onto the surface of the white dwarf, it builds up a layer thicker and thicker and thicker until the pressure and the temperature get high enough that it undergoes a thermonuclear explosion and blasts that layer of matter off into space. In fact, the difference between erupting stars and pulsating stars is very important and led to one of the most important discoveries of the last couple hundred years in astronomy, that is Hubble's understanding of the expanding universe. So we really need a movie, and we finally designed a telescope to do that. The Vera C. Rubin Observatory is in the Andes Mountains in Chile, one of the best places in the world to observe because of the sky conditions, and there it is seen from a helicopter. Here's the primary mirror arriving. It's 27.5 feet across. It's a pretty big telescope. Here are the people celebrating the installation of the secondary mirror, which is an unusual shape. It's hard to tell which of these are real people and which of these are mirror images, but the mirror is extremely precise. So here it is being installed. We're getting ready. It's only a few months until we get first light with this telescope. And here's the camera. It's a pretty big camera. It's thousands of megapixels. It weighs thousands of pounds. It's going to take 2,000 images every night. And the consequence is that it's going to produce 20,000 gigabytes of data every night, 365 days a year, over the course of a decade. More data than all of astronomy is collected in all of our human history. And what that's going to allow us to do is literally to make a movie of the sky. Now we're lucky if we see 1 or 2 or 3 stars exploding, stars erupting, stars eclipsing in any given night. But this is expected to see hundreds of thousands, if not more than 1 million such events every single night. It's going to give us an entirely different view of the universe. Instead of static images, it's going to be a movie.